0 volts. So it says, the next question says, an electron is released from rest at the negative plate. What is the speed when it hits the positive plate? So you release an electron from here. The initial speed is 0. And it's going to be repelled by the negative plate, it's going to be attracted by the positive plate, or it's a negative charge sitting in an electric field that points to the right, the force is going to be to the left. So it's going to go this way, and the question is, what's going to be the speed when it hits over here? Right? And, well, they don't say it, but, you know, the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So how do I do this problem? It's a conservation of energy problem, right? So I say the initial energy. I don't want to call it capital E because you might confuse that with the electric field. So I'll just write down the word. Initial energy equals the final energy. And I don't call it mechanical energy because this is kinetic energy plus electrical potential energy, when the electrical potential energy is not mechanical. It's not a spring, it's not gravity, it's just not mechanical. So I just call it energy. So initially, it's 1/2 mv initial squared, but it starts from rest, plus. What is the initial electrical potential energy of the electron? Let's say the charge is Q, which is minus 1.6 times 10 to the minus 19 coulombs. What is the electrical potential energy of it? So it should be, what should I write down actually? Let me write down the expression and then plug in the numbers. It should be what? The charge of the electron times what? Times the potential at that point, which is the potential at, you know, well, it's really the potential at the negative plate, right? But we were told that that was 0, right? Yes? Now, when it gets to the positive plate, its kinetic energy is going to be this. This m is the mass of the electron, right? It's the thing that's moving. And what is the electrical potential energy of the electron when it gets to this plate? The potential there is V plus, and the charge is Q, right? When it gets there, what will be its electrical potential energy? It will be that charge times the potential there, generated by the two plates, right? Which is V plus. So it will be the charge of the electron times the potential at the positive plate. Now, can you figure out the potential at the positive plate? How would you figure out the potential at the positive plate? You know the electric field. You know the distance between those two plates, and the electric field is uniform, right?
Could we just do what we did earlier, but instead of the distance being 2 millimeters, it'd be 5 millimeters?
Exactly. So I can do this where V plus, right? Minus V minus, but this is 0, right? That's the potential difference, right? That's ED. But the D between the two of them. And that's what? 3.39 times 10 to the 6. And the distance between the two plates is 5 times 10 to the minus 3. So this expression becomes, you have 0 plus 0 equals. And the kinetic energy of the electron is 1/2 times 9.11 times 10 to the minus 31 times V final squared. That V is the speed, plus the charge of the electron, which is minus 1.6 times 10 to the minus 19 coulombs, times the potential there, which is just this quantity here, right? Just this. And then you solve for V. Do you see it or not see it? No? Yes, the acceleration will be the force divided by the mass. Will be Q times E. F equals, so the acceleration will be, the net force equals ma, right? So this is Q times E, right? As the charge of the electron, right? Equals ma. So the acceleration would be QE divided by m. When you plug in the sign, when you put in the charge of the electron, you remember that the electron is negative, right? So the acceleration vector is opposite to the electric field vector. And it makes sense, right? The electric field is to the right, so the acceleration has to be to the left. The particle is moving to the left, so it speeds up, as it must, because it started from rest. Right? If it started from rest and then it was moving, it must have been speeding up to get to that new speed, right? Now, that's one way. Another way to figure out the acceleration is to say, well, the force on the electron, Q times E, this electric field is the same everywhere, so it's constant. So you can use the kinematic equations. You can say V final squared equals V initial squared plus 2A delta X. So I started from rest. So V final squared equals 2 times the acceleration, which let's say you get it from there, right? Or actually, you want to know the acceleration, but you found V final from here. And the delta X is the 5 times 10 to the minus 3. So you can also get the acceleration from there, knowing V final from there, or vice versa. Get the acceleration from here, plug it in here to get V final. Or get V final from conservation of energy.
We can only use the kinematic if the E is constant.
If the acceleration is constant, which means if the acceleration is constant, which would be constant if the force is constant, right? And that means that as the particle moves, the electric field has to be of the same value everywhere in space. Because as it moves in that space, and also constant, yes. Constant in time and the same everywhere in space. Yes? I mean, let me address this issue again, okay? Because I think the word, can I erase this? Suppose you have a point charge over here, plus 3 nanocoulombs, right? What is the electric field that it generates 1 meter away? So it would be KQ over R squared, so that would be 9 times 10 to the 9th. Q is 3 times 10 to the minus 9, divided by 1 squared, right? So that would be 27, right? So the electric field here would be pointing which way?
To the right.
To the right. And the value would be 27 volts per meter, or meters per coulomb. What would be the electric field 2 meters away? Let's consider 3 meters away because it'll be easier. It would be KQ over R squared, 9 times 10 to the 9th, 3 times 10 to the minus 9 over 3 squared, right? So this cancels that and this cancels that. It would just be 3. And it will point it this way. So the electric field there is 3 volts per meter. So we can go to 1, 3. Yes? Suppose this charge is fixed. Are you with me? Good. Now I take an electron or a negative charge, right? And I put a negative charge over here, minus Q. And I let go of it from rest. Which way is it going to go? When I let it go. When I release it from rest. To the left, right? Now, suppose this charge is minus 2 coulombs. What would be the force of the charge acting on this charge over here, on this negative charge when I release it? What would be the force of that when I release it? It would be this way, right? And how big?
-6.
So it would be, well, so it would be this times that, right? So it would be 6. And the negative is to the left, right? Opposite to the electric field, because the charge is negative. So this would be 6 newtons. In fact, it's better to think of this as newtons per coulombs, because then you'll see that you multiply them to get, so this would be newtons per coulombs, this would be newtons per coulombs. Yes? That's going to give that electron an acceleration. And it's going to then, to the left. It's going to move to the left. When it gets over here, right, not an electron, the negative charge, when it gets over here, what will be the force on it? It's going to be to the left, but how big? Hmm?
81 newtons.
So what's the answer?
For at 1 meter, wouldn't it be 81 newtons? Because it's. Or wait. I think that's wrong.
What will be the force?
Oh, it's -2. Oh, I thought it was
on
-3.
this charge?
Oops.
Right, it's minus. In fact, let me do this. So maybe that's confusing. What will be the force on it?
54 newtons.
What is it? And the negative is this way, right? I'm showing the vector like this, right?
Should we say 54 negative I hat?
So if you want to write it, you can say, okay, so this is minus 54 newtons I hat, and this one. But I got the direction over here, right? So I write the magnitude and the direction. But the point I want to make is this. I don't care what this charge is doing. Right? This charge, this negative charge, is moving in the electric field of this one, right? What is the electric field over here generated by this charge? And this one stays there, this one. This one stays there. What's the electric field that it generates over there? 27 newtons per coulomb to the right. All the time. So it's constant. As that one moves, this one is 27 newtons per coulomb to the right all the time. Right? Over here, what is the electric field there generated by this one? It's 3 newtons per coulomb to the right all the time. So throughout this space over here, around this charge, the electric field has different values, right? Because it's at different distances away from the charge. But whatever those values are, they stay the same as time goes on. Right now the electric field over here is 27 newtons per coulomb. 2 seconds later it's 27 newtons per coulomb. 2 seconds more, it's 20, So everywhere in space over here, the electric field stays the same. But that doesn't mean that it has the same value at different points. So saying that it is constant means that as time goes on, the value of that electric field at some point stays the same. But it is a non-uniform electric field because at different locations in space, the electric field has different values. So it is non-uniform, but constant in time. So the word constant, people sometimes use it to mean uniform. And uniform, so there's a difference between uniform, what uniform means, and what constant means. Yes? Now, in this case, you could say, well, like the comment that she made a little while ago. The acceleration is constant because the electric field is constant. It's not because it is constant. It's because the electric field in this problem is the same here, there, and the force will be the same. And the same force, if the force is always the same, then the acceleration will always be the same. But in this case, as this charged particle moves closer, the force is changing. The electric field stays constant. The electric field there stays constant. This one stays at 3 newtons per coulomb to the right. This electric field stays at 27 newtons per coulomb to the right. They stay constant. They don't change. The electric field here doesn't change. The electric field over there doesn't change. But the particle is going to new locations where the electric field is different. Not because it is changing as time goes on, but because the particle is going to new locations where the electric field is different. And because the electric field is different here than there, the resulting force on the particle is different. And that difference, the fact that the force itself is changing as the particle moves in space, that makes the acceleration not constant. So in this problem, you can use the kinematic equations, even though the electric field stayed constant. Now, do you mean, is it constant the same here as there? The word, if it is the same here, the electric field, and there, then you shouldn't say constant, you should say uniform. I hope you, that again, right?
That's the same case for
And it's the same thing over here. If I go over here, the electric field 1 meter away, the electric field is going to be 27 newtons per meter that way, newtons per coulomb that way, away from the charge. And 3 meters away, it'll be, 3 newtons per coulomb that way. So in space, right, this expression tells you that the electric field of a point charge only varies with distance away from it. But if the charge stays put, whatever the electric field is over here, it'll stay the same as time goes on. So it is constant there. It is constant there. Now if you move in space from here to there, the electric field is going to be different. Because the charged particle generates an electric field that's different at different locations. But not because it is changing with time, it is because you're moving to new locations, which is different. So the electric field is generated by the point charge is non-uniform. But if the charge stays there all the time, the electric field here is always going to be 27 newtons per coulomb to the right, all the time. So right there, the electric field is constant. The only way for me to change this electric field is if I move that charge, so that it's a new distance to that point. Yes? Yes?
Could you please go over when it will be non-constant but uniform?
Suppose that uniform but not constant, did you say?
Yeah. Or is there no such thing like that?
Uniform is the same everywhere in space. So for example, suppose we consider this room. Well, suppose this is the Earth. That's the Earth. Suppose this is the Earth. Well, the room, right? What's the gravitational field here? 9.8 meters per second squared down, right? What about over here? 9.8 meters per second squared down, right? What about here? 9.8 meters per second squared down. So it's uniform. And what is it right now? 9.8 meters per second squared down. What about now? 9.8 meters per second squared down. What about now? 9.8 meters per, so it's constant. So it is constant and uniform. Suppose that for some weird reason that we don't know about, something is happening at the center of the Earth where mass is being made. I don't know, somebody's sneaking in mass in there, right? So what would happen is that as the mass collects at the center of the Earth, what's going to happen to the gravitational field in this room?
It's gonna increase.
So it might change to, let's say, 11 meters per second squared, but it's going to be 11 meters per second squared everywhere in the room down. So it's uniform. But as you put more mass, it's going to go to 12 meters per second squared down. It's uniform, but now it's a different value. It's changing with time, but it's uniform in this region. That would be an example of uniform, because it's the same everywhere in the room, but not constant. Because the source, something is happening to the source that's making it stronger, 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 or weaker, 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 weaker. But everywhere in space at that one time is the same. For example, what if I take, somehow I have this charged plates, right? What if I connect wires over here, and I begin to deplete those charges? In here, the electric field is going to stay uniform, but it's not going to be constant, because I'm changing the charge per unit area. As I change the charges on these plates, everywhere in here, right, the electric field is going to be uniform. But as time goes on, as I change the charges on the sources, like changing the mass of the Earth, right, then it'll be the same everywhere, but a few seconds later, it'll be different, but it'll be the same everywhere, but with a new value, because now you have a different source. That would be an example of that I can think of. Did we finish that problem or no? I don't know if there's other parts to it. But that problem, set of parallel plates, the electric field if oppositely charged, right? The electric field outside is going to be 0, and the electric field in between them is going to be something. Because there is an electric field in there, there's going to be a difference in potential. And actually, that problem turns out to be a very important problem. I'll just say this relatively quickly. In the next chapter, 24, we're going to consider one of these plates and the other plate, and you put, let's say, plus Q here and minus, or let's just say the plates are like that. So two very large plates close together with vacuum in between, some vacuum. And then we're going to take this plate, it's a metal, right? We're going to connect it with a wire to a battery. I'm sort of going to draw like a AA battery type of thing, and wire like that. So this is plus, this is minus. This is a battery. Now, what will this battery generate in this wire?
Current.
Resulting from an electric field generated by it, right? So this positive charge, right, is going to generate an electric field away from it, right? Away from it. What about that one? An electric field towards it, right? Notice how that's a very important thing that comes up again and again and again and again and again until you vomit, kind of. It's an electric field this way, right? Now, then we're going to say, well, this is a wire with it's a metal, and in this metal there are electrons that are not tightly bound to the nuclei of those atoms, so you'll have what's called a free electron. Not free because you don't pay for it, but because it has the freedom to hang out wherever it wants to hang out. Except that when it is subjected to an electric field generated by this external source, right? What will be the direction of the force exerted on that free electron by this electric field generated by the battery? Which would the electron feel a force? Should we say down the wire or up the wire? Which way?
Down.
How do you know?
The electron is negative and it's going against the earth.
Exactly. So F, that's one way of looking at it, right? The electron is negative, so the force of the electron is going to be opposite to the electric field. Or you could say it likes the positive charge and it hates the negative charge, so either way the electron is going to go this way, right? And what do you think this electric field is going to do to electrons over here? It's like it's going to pull them from that plate. And as electrons leave this plate over here, well, the nuclei of the atoms will have more protons than the electrons in that area. So what will happen is that this will become positively charged. Now what about over here? What happens to a free electron over here?
Gets pushed away.
Which way is it going to experience a force?
Gets pushed away from the negative terminal.
This way, right? The force is going to be this way, as this one was forced that way. And what will happen is that electrons are going to come this way, and they'll accumulate on this plate, which was initially uncharged, and you have an accumulation of negative charges. And there you have a set of plates that are oppositely charged. Now the electrons are not going to cross the bridge, because there's a bridge. There's like a river with alligators in there, and they stop, so they cannot. So what will happen is that this will obtain a positive charge and a negative charge. And now what you have is a capacitor. This is called a capacitor. Two conductors separated by some distance, right? With some dielectric material, insulating material in between, is a capacitor. So now you have a charged capacitor. So you see, the set of plates becomes important in some circuits, right? Now, so what you're doing over here is you're storing charge in this capacitor. Both of them together are called a capacitor. Two metals separated by the electric material, insulating material, is a capacitor. So you store the charge in there. You store energy in there for when you probably want to use it later. In the old days, I don't know, before you were born, there were these cameras that, let's take a picture. And then you would say, oh, okay, hold on, let me set up the flash. And then you would go click, and let me turn it on. And then you would wait. When you were waiting, when you went click, you connected the battery to this capacitor, and as you were waiting, the capacitor was charging. And then when it finished charging, because what's going to happen as too many of these electrons pile up over here, what's going to happen to the other electrons that are coming in? What are these electrons going to say? Dude, there's no room over here for you. We're full over here. So then the flow of charges will stop. And that's when it's fully charged, right? Like, there's so many people in here, go away, there's no room for you. So and then when the charging process stops, then a little light turns on. Oh, the flash is ready. Take a picture. Okay, and then smile. And then when you went click, when you press the shutter button, what you were doing is you were disconnecting this wire and connecting it to, something else. And connecting it to this one here, and then there was a big rush, because these electrons want to be with this plus over here. If you make this connection when you went the click, then these electrons want to go there, and it happens, and that releases energy in the form of light, and that's the light that illuminates what you're taking a picture of. That's the flash. Yes? So, anyway, in chapter 24, we're going to now consider electric circuits, and this conducting wire, though, is not going to be in electrostatic equilibrium anymore. There's going to be a potential difference. Yes?
It's kind of off topic, but I thought capacitors were coils. Or are they coils and then?
No, those are inductors. Capacitors, the definition is two metals. Yeah. So it's two metals, and you can roll them like that.
Oh, okay.
But you gotta put some dielectric insulating material, because the idea is to keep these charges away from one another.
Right.
Because if they touch, that's it. It uncharges.
Because it's more effective with rolls, like bigger capacitors.
Right.
That's why.
Okay, we have a date on Monday, right?
Yeah, I know. Yeah, I'm looking at circuits.
Yeah. But like, I use circuits with small capacitors, and they're literally just look like this.
Oh, I've only seen the ones that
Catch up
the
as soon
cylinder.
as possible, so that then you enjoy studying for the